K218b, A World Beyond. The James Webb Space Telescope, or JWST, stands as humanity's most advanced tool for peering into the vastness of the cosmos. Its purpose is not only to study nearby celestial objects but also to unravel the mysteries of distant stars, hidden exoplanets, and the very architecture of the universe itself. When scientists turned JWST toward a star located roughly 120 light-years away, they hoped for new insights, but what they found was beyond expectation. The telescope detected clear chemical evidence in the atmosphere of a planet orbiting that star, a discovery that shook astronomers around the globe. This planet is known as K218b, a world unlike any in our solar system. It resides far beyond the reach of our spacecraft, orbiting a cool dwarf star called K218, and it has quickly become one of the most intriguing targets in the search for life. K218b is a giant compared to Earth. It is about 8.6 times more massive, and its diameter is roughly 2.6 times larger than ours. Its immense size places it into a rare category called a sub-Neptune, a type of planet missing from our own solar system. This makes K218b invaluable to researchers, as it provides a glimpse into a kind of world that may be common in the galaxy yet unfamiliar to us. When JWST examined its atmosphere, it found a rich mixture of gases dominated by hydrogen. Among these gases were two crucial compounds, methane and carbon dioxide. On Earth, these molecules are tightly connected to processes that sustain life. Their detection on K218b sparked immediate excitement, as they hint at the possibility of liquid oceans beneath the planet's thick atmosphere. Even more intriguing was a faint signature of a rare molecule, dimethyl sulfide. On our planet, this substance is almost entirely produced by marine plankton in Earth's oceans. If confirmed, its presence on K218b would raise extraordinary questions about biology beyond Earth. However, scientists remain cautious, as further observations are needed to verify this early detection. The orbit of K218b is another striking feature. It lies within its star's habitable zone, the region where temperatures may allow water to exist as a liquid. This zone is often referred to as the Goldilocks zone, because it is neither too hot nor too cold. For astronomers, a planet within this region instantly becomes a prime candidate for habitability. Yet, challenges remain. Despite its promising atmosphere, K218b may be far less friendly to life than it appears at first glance. Scientists believe it could be wrapped in a thick layer of high-pressure ice, similar to what we see on Neptune, buried beneath a thin hydrogen atmosphere. Even if oceans do exist, they might be trapped under crushing pressure, making them unstable and potentially hostile to life as we know it. So how did JWST uncover these secrets from so far away? The answer lies in the planet's transit across its star. K218b is a transiting planet, meaning it passes directly in front of its star from our perspective on Earth. Each time it does, a small fraction of starlight filters through the planet's atmosphere before reaching our instruments. That starlight carries within it the fingerprints of the gases it passes through. Using its unmatched precision, JWST captured and decoded those fingerprints. Its instruments revealed the composition of K218b's atmosphere with a clarity never achieved before. This marked the most detailed atmospheric profile ever made for a planet of its type. Future observations with JWST, particularly using its mid-infrared tools, are expected to sharpen this picture even further. Researchers hope to confirm whether dimethyl sulfide is truly present, to measure the depth and structure of the planet's atmosphere, and to learn whether vast oceans may indeed lie beneath its hydrogen skies. For now, K218b stands as one of the most promising worlds for studying habitability beyond Earth. A place where science and imagination meet, and where the question of life in the universe grows ever more fascinating. galaxies and the early universe, but the legacy of the James Webb Space Telescope goes far beyond the study of single exoplanets. It is also transforming our understanding of galaxies, star systems, and the very origins of the universe itself. Recently, astronomers made a groundbreaking discovery using JWST's extraordinary sensitivity. They detected the presence of complex organic molecules, known as aromatic hydrocarbons, within a galaxy billions of light-years away. These molecules are far from simple. On Earth, they are found in coal, oil, and even in the smoke that rises from burning fuels. They are built from intricate rings of carbon and hydrogen atoms, and their existence is often linked to life-related chemistry. What makes this discovery astonishing is not just their complexity, but their age. These molecules were detected in a galaxy that existed when the universe was only about 10% of its current age. That means they formed incredibly early, just 1.5 billion years after the Big Bang. At a time when the cosmos was still young and chaotic, chemistry advanced far faster than scientists had once imagined. The galaxy in question is remarkable in its own right. Despite being so ancient, it had already grown to a mass similar to that of our Milky Way. It was actively producing elements such as carbon and oxygen on a surprisingly large scale, fueling the birth of stars and complex compounds. This challenges long-held models of cosmic evolution, which suggested that such complexity would take billions of years longer to emerge. JWST made this detection by capturing faint light that traveled across unimaginable distances. That light carried within it the fingerprints of molecules scattered in the galaxy's interstellar clouds. By analyzing those chemical signatures, scientists could map not only what existed, but also where it was distributed throughout the young galaxy. The uneven spread of these hydrocarbons remains a mystery. Why they clumped in certain regions while avoiding others is still unknown, raising new questions about how galaxies evolve. What is clear, however, is that chemical richness was present much earlier than once believed, giving rise to the building blocks of life on a cosmic scale. Every new observation pushes science deeper into the past. Through JWST, we are now able to witness the story of the universe unfolding in its earliest chapters. We are seeing how galaxies formed, how matter was distributed, and how the ingredients of life began to appear almost as soon as the cosmos allowed it. These findings tie directly into humanity's oldest questions. Are we truly alone, or are we part of a universe where life may have emerged in countless places? How did life first spark on our planet, and could it follow similar chemical pathways elsewhere? And as the universe expands into the unknown, what ultimate fate awaits it, and us? The James Webb Space Telescope does not answer these questions outright, but it brings us closer than ever before. By unveiling exoplanets with promising atmospheres and galaxies filled with unexpected complexity, it is rewriting the story of creation piece by piece. It shows us that life's essential elements may not be rare, but rather woven into the very fabric of the cosmos. With each discovery, JWST expands the horizon of human knowledge. It opens windows into the past, illuminates the possibilities of distant worlds, and deepens our appreciation of the vast and intricate universe we inhabit. Step by step, light by light, it reveals that the answers to our greatest mysteries may already be shining among the stars.